Hey guys, this is Mainak, and today we'll see how to design rise and tread type staircase in manually. And you know, you have an architectural plan and you want to design the rise and tread type staircase. So we all have read how to design the staircase. So briefly, we'll see with the help of practical live example of how to design the staircase. So first of all, when you have a staircase like this in front of you, so you can see there are the sections and or everything else available. And when you see the staircase available like this is a kind of a quarter ton staircase. It is not a dog leg staircase. So first thing you need to do is you find the flight having the maximum number of risers. So you can see the 11 risers. You can see easily this is the span which has the maximum number of risers. This is 11 number of risers, and along with the slab. So we take this detail, we take all the lengths and everything, and then we design the staircase as per our general method. And if you can prepare an Excel sheet later, then it will not be able to, you'll be able to do it, okay, automatically. But I'm showing you the manual design for now, okay. So you can see these are the two landings which we have here. This is a landing and this is a landing, and the middle one is the flight. Okay, so we have the lengths here 1100 and 3000, and this portion is also right side portion is also 1100 I've taken. Okay, the riser is this data has already been given by the architect, so we'll try to keep all the data constant and not change any. If any emergency situation, if anything is required, then we can change. So riser is 150 and tread is 300. It is given. So riser plus tread square is equals to 335.4. So this is the that an effective length of the flight is 3 meter, which is the flight actual length plus this width of this landing or width of the flight. That is 4.47 meters. Now assume thickness of the riser can be taken as L by 25, which is 164 mm. If we didn't have anything, we would take 160 mm, but the architect has taken 150 mm. So I'll take 150 mm, try to make it pass in 150 mm. Okay. So if the effective if the thickness is 164 or 150 mm, then the effective depth D will be 150 minus 20 mm, which is the cover. And if we take maximum 10 mm bars, then 10 by 2. So why I'm taking 10 mm bar? Because in 150 mm bars, if you just see the rebar, it is easier to bind 8 mm then 10 mm, and 10 mm then 12 mm manually. So since this is going to be a project in which this 150 mm bar is involved, so for the easier binding and easier this thing, so I'm taking 10 mm bar. So I'll try to just make the structure pass by 10 mm bar. So it just comes as 125 mm. So now the first step is the load ongoing. So load ongoing, obviously self-weight is involved, and you can see the formula which is easily written: unit of concrete into riser plus tread into effective depth by thickness of the tread. So it comes this floor finish as per IS 875 part uh, you know 2. That is for the live load. You can take floor finish. Okay, floor finish for the dead load. Sorry, you can take as 0.5 for the tiles, marble, and this is given in 875 part 1, and live load is given in 875 part 2. You can see for normal or residential buildings, 3 kilonewton is advised for live load. However, if you see in books, the 5 is taken. So in this case, I've taken less because since I'm already working with less, in depth. But you can take 5 for safety also, but 3 is okay for residential and normal staircase in which large loads are not involved. So factored load is multiplied 1.5. So the factor of safety, to increase the loads for the factor of safety. So we have the factor load on the going. Okay. Now the loads on the landing. So landing has also to be designed. So same thing, self weight. In this only we need to assume the thickness of the landing. Since the riser thickness was 150 mm and architect has also taken 150 mm as the landing, so we'll try to make the landing pass by 150 mm, which it will do because in landing there are not much loads here. So self weight, then floor finish, then live loads, same, and then we factor the load. And when you calculate the movement, for calculating the movement only, and not the reinforcement, for calculating the moment, the final load can be taken as 50% of this load. Okay. So final load is taken 50% of the factor load, which is 5.34 kilonewton per meter. So now this diagram is very important. So this is the actually the length of the flight, which is 3 meter. and 0.55 and 0.55 is the landing width by 2. Okay, and I have already calculated this particular length, because when you will calculate movement, because UDL will act in 0.55, and if I have to give the distance from the half of this span to the UDL, then I already calculated this length, that is 3 by 2 plus 0.5 by 2, 0.55 by 2, which is 1.75. Okay, so first of all, we calculate the reaction and we take one direction as positive, and reaction of on landing is the load on the landing, which is the final load 5.43 into 0.55. 0.55 is this zone in which it is acting, and plus, okay, plus that is the load ongoing 22.76, which you calculate the loads ongoing. Here you can see here 22.76 was the load ongoing, 22.76 into 3 by 3 by 2. Okay, so by 3 by 2 because it is acting in the middle. So this is a reaction load, and this reaction comes as 37.13. Now, and then we go to design moment at midspan. Now, when you design moment at midspan, simply it is the reaction into the total length in the final diagram. You can see 37.13 into 4.1 by 2. So this is the 37.13 is the reaction. Okay, this is positive. So this into the half of the length 4.1 by 2. This is the first thing. And then we have this 5.43, and for the 5.43, this is the final load on the going into 0.55, which is the length here, into 1.775. All these have already been calculated. 0.55 and into 1.775. This is the distance. So 0.55 is the distance in which the load is acting, and 1.75 is the distance from the center. So this is the case. And then it is the normal formula WL square by 2, where L is the span of the flight, which is the 3 meter. So 3 by 2 is 1.5, 1.5 square by 2. So this is acting here, and this comes as 45.22. So as usual, we have this very important formula: AST by BD is equal to FCK by 2 into F by 1 minus root over 1 minus 4.6 into MU by FCK BD square. So we have calculated MU here. So we just put MU, and we take M20 grade concrete and Fe500 steel, and we find the AST required. So AST required is this much, 1000 mm square per meter, and for 10 mm bar, if you do pi by 4 into 10 square, it comes as 78.5. So the spacing, required spacing is 78.5. So you can give 75 mm spacing for the ties. And for the distribution bar, this is nominal 885 provided. Normally 3 bars are provided. So each bend you need to provide this. And I'll show the final structural drawing also in this particular video. So you can see in this structural drawing which I have provided, this is the 10 mm pies at the rate 75 center to center, and this is provided here, and 3 bars of 8 mm are provided here and here, which is at each bends, and you can see 150 and 300. Now this is the in the form of rings. Okay, these are provided everywhere. Now let's come to the load of the on the landing, how we have designed this. So effective span on the is the 1.47 meter, and if you just notice this 1.47 meter was this one effective span of the landing here. So if there are 2 landings, then we have to do it little bit differently, just into 2 in a place, but effective span will be the same. Okay, so effective span is 1.47 meter. Okay, and then we are going to come here and directly calculate the effective depth. 20 mm cover, 10 mm bars, maximum bars used, so 125 mm cover, and loads on directly on landing, which is the 1.5 into factor loads. Notice that this was not the load which was half. Okay, we take the full load on the landing, factor load on landing, and from going we calculate the factor load on going into length of flight, which was 3 meter, and divided by width of the going, which was 1.47 meter, or width of the, in this case the width of the landing is also the same, 1.47 meter. So if there are 2 landings, in the case of dog-leg staircase, there will be a 2 here. So we'll just add a 2 here in the case of dog-leg staircase. So reaction is coming this much. So when we have reaction, we can find MU. MU is equals to WL square by 8, which is the the center for the UDL. So WL square by 8, we calculate the MU and simply put in the formula of the AST, and we find the required AST. Required AST is 300 mm square per meter, and 78.5 is 5 into 10 square. So then we find the spacing of 10 mm bar, which comes as 261. So 10 mm phi at the rate 250 center to center parallel to the risers given, and always for perpendicular to the risers we give 150 mm center to center. This is nominal reinforcement. So this is not design, this is nominal. Okay, that's why we given 10 T at the rate 150 center to center has been given here. I can see nominal, and 10 T at the rate 250 center to center. Okay, just showing you again. Okay, 10 T at the rate 250 center to center has been given here. Okay, at the perpendicular to the risers here, which has been given. Okay, and in the top again we provide nominal rebar of 10 T at the rate 200 center to center. So design this, we have designed this, and this one is provided nominal, this one is also provided as nominal, this one is also provided as nominal. We have designed this. So these are the things, and you need to provide landing beams, or you can provide a 10-inch wall for supporting the landings at the staircase location. So this is the a practical example of a staircase design. If you have the architectural plan, if you have the elevation, or even if you don't have the elevation also, you can make this easily, and you can provide like this so that the drawing is easily executable at the site. So thanks for watching. Hope you've learned something new today. Keep learning. Bye bye.